Welcome to the CUAHSI Cyberseminars conference call. My name is Anthony and I will be your coordinator for today. At this time, all participants are in a listen-only mode. We will be facilitating a question and answer session towards the end of this conference. If at any time during the call you require assistance, please press star followed by 0 and the coordinator will be happy to assist you. I would now like to turn the presentation over to your host for today's call, Mr. John Duncan, Communications Director. Please proceed, sir.
Thanks, Anthony. Welcome, everyone, to today's Cyber Seminar, the second of this week, and thanks again to those of you bearing with us through our technical difficulties with these. For those of you who are new to this, I'd just like to quickly go over some details. If you have any technical problems today, you can use that chat box on the lower right-hand side of the screen to send a message to me, the host, or anyone else for that matter if I'm whispering in the back of the room. If you have any feedback on the series, how things are going at your campus or your institution, we'd love to hear about it. That can be done by sending an email to commanager@CUAHSI.org. This presentation can also be downloaded from our website by following the Cyberseminar link. And if you have any technical difficulties today, you can go through that in Adobe format, PDF format. Just realize that some of the animations may not come through in some of the ones that have been archived before. So the schedule's been shuffled around a little bit. We don't have any seminars next week, but the week after Thanksgiving, on that Tuesday, Manu Law from Columbia will be presenting on hydrologic change detection. The Wednesday, December 1st, David Altus from NCAR will be presenting on advancing coupled land atmosphere prediction, and we're still looking for a date for Jeff McDonald's talk. With the updated calendar and links to the draft papers and presentations and the discussion forums that we started this semester can all be found by following that Cyber Seminar link on the CUAHSI homepage. I'd now like to introduce today's speaker, Dr. Henry Lin, who is an assistant professor in the Department of Crop and Soil Sciences at Penn State University. He received his bachelor's in soil science and agrochemistry from Fujian Agricultural University in China, his master's in soil science from Nanjing Institute of Soil Science, also in China, and his PhD in the same discipline from Texas A&M University. His research interests include integrating geospatial technologies, environmental modeling, artificial intelligence, and web-based tools in soil and water studies, as well as hydropedology, about which we'll be talking today. It's my pleasure to introduce to you Henry Lin.
Thank you, John. I hope everyone hears me okay.
It's a little bit faint actually now, Henry. Can you turn up your volume?
Okay, is that better now?
Not much.
Is that, how about that now?
It's a little bit faint still.
Huh. Well, that's pretty much what I can do.
That sounds better.
All right. Well, I'll put my more closer to a speakerphone then. Good afternoon, everyone. Let me start by saying thank you for your participation in this cyber seminar. It is my pleasure to have this opportunity to represent our vision team to share with you what we come up with. The title of our vision paper is shown on the slide, Hydropedology, Synergistic Integration of Pathology and Hydrology. I would like to acknowledge our team members listed here. As you can see, it's a good mixture of biologists, physicists, hydrologists, and others, such as geographers, system scientists, and groundwater hydrologists. I will skip reading the names here. The interest and support of all our team members is greatly appreciated. In particular, just listed here who co-authored our vision paper, the Homebomber of Wageningen University in the Netherlands, Jacob Paczewski of USDA in Delaware, Maryland, Andrew Weston of University of Melbourne in Australia, Jim Thompson of West Virginia University, Lynn Van Newton of USDA in Riverside, California, Hans Jörg Vogel of University Heidelberg in Germany, and Alan Lilly of Macaulay Institute in Scotland. In this presentation, I would first provide some introductory information, including knowledge gaps that we identified. Then we would look at our research vision, including critical concepts and challenges associated with hydropedology. And then I would briefly discuss 3 interlinked strategies for achieving our vision. And finally, just brief statements about expected. So briefly, first introduction. As we know, soil is a geomembrane across which water and solids, as well as energy, gases, solids, and living organisms are actively exchanged among the hydrosphere, atmosphere, biosphere, and lithosphere. The critical role of soil in many hydrologic processes are obvious, including, for example, watershed hydrology, eco-hydrology, land-atmosphere interface, and hydrogeology. Indeed, soil and water interaction creates the fundamental interface between the biotic and abiotic, and hence is a critical determinant of the state of the Earth's system. Now, as you know that with the current booming of hydrogeosciences, we are encountering a new intellectual paradigm that emphasizes connections between the hydro system. While hydrometeorology, eco-hydrology, and hydrogeology are well recognized, it seems that an important missing piece of the puzzle is hydropedology. Okay, here we go. That focuses on the interface between the hydrosphere and the pedosphere. Well, before I go further, I would like to clarify the term pathology here, just in case some of you might have a different interpretation of it. Here it refers to a branch of soil science that integrates and quantifies the morphology, formation, distribution, and classification of soils as natural or anthropogenically modified landscape entities. Now, as a background, I'd like to touch a little bit on the different views of soils. Traditionally, the surface view of soils might be more like a granular shape, either grass beads or ground and seed soil materials. Only in recent decades has the shift to the field regime begun, where physicists pay more attention to in situ soil structure, preferential flow, and spatial and temporal variability. Hydrologists, on the other hand, often treat soils as more or less homogeneous in layer in their models. Pathologists, meanwhile, have a focus on patterns as observed in the landscape and have placed a much greater emphasis on the vertical relationships of horizons and soil processes up to about 2 meters of the Earth's surface than on the horizontal relationships, although the horizontal relationships are what they attempt to delineate in soil mapping. Now, in terms of time dimension, pathology often deals with much longer time scale than soil physics, with hydrologic time of in situ, with kind of connection among the three. So, wouldn't it be nice to have the three integrate so that we have a better view of the world? Another missing link is the so-called unwanted zone, the deep veil zone, and the capillary fringing. The Earth's critical zone concept promotes the integration of hydropedology, hydrogeology, as well as land-atmosphere interface and eco-hydrology. Now, to truly analyze pedology with hydrology, we need to debug stereotypizations on both sides of the fence. For example, to many hydrologists, pathologists use strange names, taxonomic names to describe few soils, and they make empirical statements about soil functions based on observations that are not necessarily supported by measurements. But on the other hand, pathologists are taken back by the simplified representation of few soils in terms of homogeneity and isotropic that hydrologists often assume in their models, which to pathologists clearly does not adequately reflect real-world conditions. Pathology has its roots in soil survey that considers soil landscape relationships and soil structure. These two aspects are critical for surface and unsaturated zone hydrology in order to improve quantification of flow regimes in the field. However, the pathological knowledge is often conveyed as semi-quantitative statements. Pathologists thus can benefit from soil theories in hydrology that when transforming qualitative descriptions into quantitative expressions that are increasingly in demand from diverse users of soil survey information. Please allow me to take a moment to remind ourselves just exactly what is soil. To answer this seminal question would require a good understanding and appreciation of this gift from nature and its essential characteristics in the landscape. For example, here's a major agricultural soil in Pennsylvania called Henderson Slope Loam. There are many stories we can tell about this soil just by looking at its soil profile. So just, for example, from the top to bottom, here is, well, because of continuous piling, here's top-hand with plated structure formed in the surface soil, while the same soil series under grass has fine subangular blocky type of structure in A horizon. So these two structures are very different impacts on water flow direction and flux. Now, another feature that is obvious, you can tear water flow and more holes, even down to 80 100 centimeter depth. So they are apparent multiple flow contours. The third feature that I would like to point out is the preferential flow marks as indicated by the black manganese masses on packed surfaces, and also shiny packed surfaces with water fumes. When you are out in the field in situ, you can tear that easily. Now going further down, you also see some window features and great colors on the surfaces of limestone rock plastons, the parent material of this soil, suggesting some kind of water stagnant situation near the bottom of this soil profile. So, then what is the soil? Well, I try to point out these three aspects that warrant close attention. All three are in the domain of pedology. The first one is called pedology, including pet strength, pet size, and pet shape. Pedology, along with the interrelated porosity, are the essence of soil architecture or soil structure that is influenced by the 5 interacting soil factors in the landscape sphere and is governed by the interrelationships between inorganic and organic constituents and physical, chemical, and biological processes at a macro and microscopic scales. Indeed, the word PED, P-E-D, is well reflected in the term pedology. This first essence of natural soils may be summarized as the need to get back to soil structure. Second, layering of soil horizons, which has at least 3 significant implications for hydrology. First, any interface between soil layers, either K over sand or sand over K, will slow down water downward movement. 2, soil layering promotes lateral flow, particularly in sloping landscape with water restricting. So horizons of different textures and structures often lead to preferential flow. And this could be summarized as getting back to field reality. Now the third one that I like to highlight here is soil landscape relationships, which are the foundation for mapping, classifying, and modeling soils. Landscape evolution has a lot to do with the fluid flows of water, chemicals, and energy, that is, the hydrologic cycle. A systematic understanding of soil landscape relationships would facilitate the formulation of conceptual and mathematical models of landscape hydrology. So this could be summarized as the need to get back to landscape. In our vision paper, we identified multiple logic gaps that could be addressed by the synergistic integration of pedology and hydrology. And here's the first one: prediction of preferential flow dynamics and pathways in different, at different scales. Their interface with the soil matrix, their resident times, and their significance in different soils and landscapes remain unresolved. Hydrologists may not have a clear picture of flow pathways in the unsaturated zone before starting modeling or field experiments. But on the other hand, pedologists routinely document in situ pedological features such as K-fields, tech coatings, flow structures, root distributions, and hydromorphic features, etc., that often indicate preferential flow paths and soil drainage conditions. Thus, a concerted effort is needed to quantify soil natural architecture in a manner that could be incorporated into flows, the models of flow and transport and their steering. When, where, and how water moves through landscapes and its impacts on soil processes and subsequently soil spatial patterns. Currently, many hydrological models do a poor job in predicting subsurface lateral flow and base flow versus runoff in total stream flow. But as you know, sloping topography, stratification, and soil layering, especially water-restricting layers like vegetation, all favor lateral flow. The convergence of surface and subsurface lateral flows within a landscape results in the formulation and distribution of streams and rivers and contributes to the spatial heterogeneity of soil and vegetation across the landscape. The next logic gap is bridging multiple skills, which remains at the heart of many hydrologic and pathologic studies. Pathologists study both the mechanisms and the magnitudes of soil spatial diversity as a basis for broad generalizations of soil genesis, classification, and mapping, whereas hydrologists have also long been concerned with the scale and spatial temporal variability of hydrologic processes. However, the convergence of these efforts has not occurred. Large-scale efforts of pathologists and hydrologists will share light on appropriate procedures for multi-scale bridging. For example, paleogenesis is an integrated phenomenon resulting from a series of physical, chemical, and biological processes. Hence, to provide a holistic view of the system evolution and hydrologic processes that might have occurred or are occurring at the Earth's surface and near-surface environments. Well, as you know, hydrologists need soil hydrologic parameters in their models and information to specify flow pathways, but such data are often lacking or difficult to obtain in large volumes. In the meantime, many national and regional soil survey databases developed over the last century have been underused in addressing environmental and ecological issues. Include procedures to extract useful information from the available databases and to enhance soil survey interpretations for flow and transport characteristics in different soils are. Bridging data gaps through approaches such as data transfer functions will be continuously in demand, which will enhance the value of soil survey databases and provide hydrologists with model input parameters. The combined efforts from pathologists and hydrologists will open up opportunities for building mutually beneficial common databases. The another logic that we listed in our vision paper is described here. Basically, hydrologists often believe that pathologists tend to view the soil as a static entity as they categorize soil characteristics into non-organic entities, such as grouping soil inherent generally into well and fully drained classes. This is yet another misperception. Suitable understanding of the implications of these terms for predicting the height and duration of water logging within the soil, as well as temporal changes in soil water regimes in the medium to long term. However, this is not always clearly communicated. Water table fluctuations in soil influence soil water storage capacity and therefore runoff and other hydrologic response such as hydrographs, base flow, solid concentrations in aquatic systems. Regular temporal sampling frameworks are becoming recognized in pathology, and conserved efforts from pathologists and hydrologists can lead to more complete data sets that will include extreme events such as sediment and solid concentrations in peak flow or sustained drought. So a move towards continuous sampling or monitoring of the unsaturated zone will provide better data sets for hydrologic modeling. So the development of pathology for physics and hydrology and other related bio and geoscience are now converging at several fronts. So the time seems to be right for us to integrate these disciplines to create a synergy. Well, indeed, pathology has a lot to offer to hydrology, soil physics, and vice versa. For instance, soil mapping provides the classical foundation for our understanding of soil variability over the landscape. So topographic descriptions have been a major source of in situ soil structural information and various soil hydromorphological features that are signatures of soil hydrology. Soil survey databases provide a wealth of information that hydrology could utilize So classification offers a hierarchical system for organizing, modeling, and transferring our knowledge about this, provides insights regarding soil evolution over time. On the other hand, soil hydrology is a major driving force behind pathogenesis for morphology and soil distribution. It controls a variety of physical, chemical, and biological processes that lead to the formation of different soils and diverse land uses. So moisture and temperature regimes play a critical role in classifying soils, and a spatial and temporal distribution of water provides clues to soil variability and how we map soils over the landscape. Furthermore, with increasing emphasis on human impacts and then management practices, the rising interest in dynamic soil properties will require more attention to soil physical and hydrological properties. In that context, hydropedology has been suggested as an intertwined branch of soil science and hydrology, or a bridge connecting the three pedologies of physics and hydrology that embraces multi-scale approaches to study interactive pedologic and hydrologic processes and their properties in the unsaturated zone. Here, in a vertical direction, hydropedology in combination with hydrogeology suggests a more integrated and holistic approach to study water, soil, and rock interactions in the critical zone. In the horizontal orientation, hydropedology attempts to connect the pattern and the landscape paradigms to address multi-scale bridging from microscopic levels such as the pole scale, soil aggregate scale, to mesoscopic scale such as patterns and patinas, and to macroscopic scale such as watersheds, regional and global levels. In essence, hydropedology promotes this bridging disciplines, skills, and data. Bridging disciplines requires a close ally among biology, physics, hydrology, and other related bio and geosciences such as hydrogeology, geomorphology, and ecohydrology. Bridging skills suggests transferring our knowledge from the lab to the field, to landscape, and eventually to regional and global levels. Bridging data implies translating existing databases, such as social databases, into useful information, and then from information to generate knowledge, and then technology to help facilitate decision making. Now, fundamental scientific uses of hydropedology have been suggested to include at least the most listed here: soil structure and layering as indicators of flow and transport characteristics in natural soils, soil morphology as signatures of soil hydrology, water movement over the landscape of different spatial and temporal scales in relation to soil cover, and hydrology as the factor of soil formation and the driving force of soil dynamic changes. In the interest of time, I will not further expand on this. Well, now let me discuss our research vision after this kind of background information I thought would be helpful for understanding our critical concepts presented here. Overall, 12 scientific hypotheses have been suggested in our vision paper. All of them, however, require vigorous testing and concerted efforts from pathologists and hydrologists and other related discipline scientists. Among them, 6 are kind of critical concepts and challenges for advancing hydropedology and for enhancing the prediction of landscape water flux, including holistic conceptual frameworks, quantification of hydrological structures, identification and prediction of patterns, bridging multiple skills, multiple evidence and robust models, and human impact. The other 6 hypotheses are related to unique contributions of hydropedology to the advancement of hydrology and pedology, including soil morphology, and soil structure, pathogenesis, classification, mapping, database, and future pathology. Now let me elaborate each of these a little bit more. First is the holistic conceptual framework, such as the one illustrated here. This is not the only one, but just for illustration purpose, I discussed a little bit more here. At each scale, structure reflects spatial arrangement, much like our road highway system. Function is the result of fluxes or processes, much like traffic condition. the two-way communications between the structure and the function is dictated by basically steer, which also in spatial variability and temporal dynamics of the system. The model supposedly at each scale or at multiple scales strives to integrate structure and function so that the patterns and dynamics can be explained and predicted. The challenge apparently is to build this kind of bridges that connect different skills. Shown here is the sketch of a conceptual model illustrating dominant flow pathways along a hill slope in forested catchment in central Pennsylvania. Dominant flow pathways are indicated by the blue arrows, and also typical soil pour for moisture along this soil catena. The moisture content is indicated by the width of this light blue chart. All right. The main flow pathways illustrated here are this one flow at the interface between the bottom soil and the weathered shale, the bedrock of this soil. The other one is subsurface bubbling seepage or microbe type of flow underneath the surface. Now, in terms of surface runoff, that occurs only occasionally at the base of the hill slopes during big storms or snow melts. In most cases, that doesn't happen in terms of the overall runoff. So our first hypothesis proposed in our vision paper is this: systematically designed and integrated hydropedologic studies across multiple scales and geographic regions result in appropriate quantification of the proposed holistic conceptual framework. The first is quantification of hydrological structures of soil hydrologic systems. Now, illustrated here are concepts of scales and spatial heterogeneity in the soil system and in the geology system. To illustrate using soil structure, here is a regular soil profile photograph. Here is X-ray computing tomography of a portion of A horizon, and here is X-ray microtomography of a small portion of soil matrix. The corresponding images are segmented into structural units, such as, in this level, dense aggregates in gray, within loose matrix in white, and few metropoles in black. Fractal model might be one of many possible models useful for quantifying soil structure range. So our second hypothesis proposed is this: soil systems exhibit hydrological structures, either discrete or continuous, that can be quantified using soil landscape expertise, coupled with a set of measurement techniques, either non-invasive or invasive. The third critical concept and challenge is identification and prediction of patterns or spatial temporal organizations of structures and functions. Illustrated here are two simulated patterns of soil moisture deficit. In a watershed study by Jason et al. In Australia, each of these two patterns has exact same mean variance and correlation length in terms of this soil moisture deficit, blue for wet and red for dry regions. But this one is random, and the other one is organized by kind of wetness index. The two patterns produce very different responses to a given rainfall input, as illustrated in the lower panel in this runoff simulation results over time. The organized pattern gives higher and earlier runoff peaks than the random case for the small rainfall events, while the reverse is true for larger precipitation events. Here, in the human study of the cholera catchment in Australia, again studied by Grayson and his group, the extensive observed TDR soil moisture data, spatial temporal patterns of soil moisture were revealed. Basically, in a wet winter, surface and lateral flow was dominant, producing a topographically organized spatial pattern like this one. While in the dry summer, there was minimal lateral distribution and fluxes were essentially vertical, not producing a kind of random pattern that was not related to topography. This kind of changeover was a reflection of the changing control on soil moisture. However, some spatial patterns of soil moisture are temporarily persistent. That is a measure of time stability. So our third hypothesis is this one. Storages, pathways, and resident times of water flux in the landscape exhibit identifiable spatial distributions and temporal patterns with possible interacting spatial and temporal dimensions. This spatial and temporal persistence of water fluxes can be used to subdivide landscapes into similarly functioning hydrologic units. The first critical concept and challenge is bridging multiple skills. The approaches may include lithographical macroscopic homogeneity, explicit hierarchy, or continuous hierarchy, or cycle models. Further exploration of this topic is currently critical. In an analog to the leaf, tree, and forest type of relationship, it is apparent that when the sample size is changed from small soil cores to few plots, we need to incorporate soil structural information and the concept of the representative elementary volume. When the sample size is further enlarged from few plots to watersheds, we need to consider the variation in topography, land use, and the concept of representative elementary area, things like that. Such hierarchy helps explain the observed differences between few measured soil hydraulic properties and laboratory determined values, and the large spatial variation in soil hydraulic properties over the landscape. So our first hypothesis is described here. Scale dependence in hydrologic parameters can be explained using hierarchical structures in soil topography and land cover. Scaling while structural hierarchies enables enhanced prediction of water fluxes across scales. The fifth critical concept and challenge is related to the need of reliable, elegant, and robust models. This is because, believe it or not, most current computer models are either too good to be real or too real to be good. In the first case, our simplification, the generality of the results. In the second case, however, the need for detailed input data renders the model impractical to apply, except in a research setting. Now, landscape hydrology is often related to soil landscape relationships. Shown here are classical soil survey block diagram portraying a soil map based on soil landscape relationships, and two contrasting landscape soil water relationships. This one is convex landscape showing water table fluctuation in different seasons and water flow direction. And the other one is concave landscape showing water and solids in the upland portion moving down into the soil profile when they either enter into the groundwater or move laterally downward, further discharge it as return flow. So our fifth hypothesis is described here. So landscape relationships is essential elements in developing elegant and robust hydrologic models. Hydrologically similar soil landscape units exist within watersheds, and these can be identified using traditional and new pedologic and hydrologic techniques. The sixth critical concept and challenge is related to human impact. This diagram shows you the distinction between major soil management types within the same soil series. use-dependent soil properties change in response to land use and management, such as soil organic matter content, microbial activity, soil structure, soil microporosity, things like that. Soil inherent properties are often use invariant that will change little with land use, such as texture and mineralogy in general. The term genome form refers to genetically defined soil theories, and phenome form refers to soil types resulting from a particular form of management in a given genome form. These two terms are closely related to the well-known genotype and phenotype as used in genetics. Such distinctions between major soil management types within the same soil series could separate in concept the reason morphogenetic properties used in soil taxonomic units such as soil series, family, order, while near surface temporal properties used in topographic units such as soil type, soil phases that are management-driven soil survey units. To illustrate, here shows you 5 land uses within a vertical called the Houston Black Clay. Y-axis is the steady state infiltration rate at zero supply tension as measured using tension tectonic is 5 land uses in the same soil series. An exponential decreasing trend, as you can see, was obvious from restored texture and native vegetation compared to soybean and oak crop management systems. The differences are reflected in cropping systems that tend to result in lower organic matter inputs, less structural stability, higher costing, runoff potentials, lower microporosity, and lower root density. So our 6th hypothesis here, the concept of genome form and phenome form combined with the use of pedotransfer functions can improve the efficacy of soil series and use as carriers of soil hydrology information under different human impacts. Now, let's look at the other 6 hypotheses proposed in our vision paper that are related to pathology. The first one is soil morphology, including soil structure. Soil morphological features and their spatial arrangement over the landscape can be used to add in determining dominant flow pathways and water fluxes through different soils and landscapes. Illustrated here are preferential flow paths indicated by either blue or red dyed in structured clay soils under low water supply tensions. Cracks or fissures, slip sides, interpedal poles, root channels, and even living roots. The lower panel shows different preferential flow mechanisms observed at pole scale, Gaussian scale, and area scale. What is shown here are water restricted vegetation in the subsoil and water preferred flow pathways along the prism macropoles. These kind of yellowish and reddish and grayish colors are what we call midostymorphic features, indicating hybrid soils. Our 8th hypothesis is described here. Pathogenesis provides valuable information regarding hydrologic processes involved in soil landscape evolution over time. Hydrology or hydropedology provides a potential means of quantifying soil forming processes. Hydrology affects and is affected by all of the 5 natural soil forming factors plus land use, as illustrated here. It is believed that organic processes are mainly driven by the presence and flow of water that may offer new perspectives into solving the factorial equation of soil formation. But to quantify such factorial models, there's much to be done and many opportunities along the way. Illustrated here are some soil macro and micro morphological features that are related to water regime and water movement in soils. There's an arctic soil with carbonate coatings, the white zone, found under arid or semi-arid condition. There's another type of phosphate flow, including iron-rich pink site here, where iron oxides have precipitated along path macropoles, resulting in macropole cracking, root restriction, escape permeability, and evidence of seasonal reduction oxidation environment. Black manganese coatings are indicating differential flow pathways. There's a big silicon site in a body soil that was caused by shrimp swell, also a potential differential flow pathway. Our ninth hypothesis is described here. So taxonomic systems can be utilized or modified, particularly when used in combination with landscape features to add in categorizing diverse soils into hydrologically similar groups. Now, pedologists have developed soil taxonomy to organize our knowledge about tens of thousands of different soils throughout the world into these 12 soil orders. Of course, the beautiful order further divided into suborder, group, grade groups, the family, series, etc. These taxonomic units may be categorized into hydrologically similar groups, particularly when they are linked to landscape features. The diverse soil types can then be mapped out for different regions or watersheds and add different skills, as illustrated here by the general soil map of Pennsylvania. Our next hypothesis, diversity as portrayed by soil maps, is the indicative hydrological heterogeneity of soil landscapes. Hierarchy of soil, hydrological units corresponds to the hierarchy of soil cover. There's an interesting illustration observation made by Pathology about 20 years ago. The soil map on 100 hectare soil in New Mexico. The bottom chart shows the comparison of measured quality statistic infiltration rate and surface soils in 20 locations scattered throughout the farm versus most estimates from soil texture using soil survey information. If the 7 soil series are ignored, there's basically no relation between measured and estimated infiltration rates. But when the infiltration rates are grouped by soil series, they have shown very high correlation. R square is pretty high. So this example illustrates that when soil map is properly used, it can be helpful to show the spatial variability of soil hydraulic properties. Here's another example from my own research catchment in Pennsylvania. The DTS soil map we developed versus the general county level simple soil map in black lines. Apparently, the county level soil map is inadapted for the catchment level hydrologic study. If we look at the moisture dynamics monitored over soil months, the differences among the 5 soil surveys identified is obvious. Okay, running down a couple more hypotheses. This one is accuracy of pedal transfer functions for hydrologic that can be improved by using structural parameters of soils and linking to soil cover and landscape features. Illustrated here are 5 general categories of pedal transfer functions that could be used to improve estimation of soil hydraulic properties for more readily available soil information and landscape features. I'm getting to know that my time is running short, so I will skip further details. We could also use pedal transfer rules for functional grouping of soils or soil horizons to estimate soil hydrologic functions. This graphic illustrates the significance of subsurface lateral seepage at the interface between A and BT horizon. When we look at the K-sub values, it is not surprising. Not only a significant drop in vertical K-sub from A to BT, but the lateral K-sub values are also much higher than the vertical ones. The last one is this one. Hydropedology is the promising direction for future hydrology. Why? Well, future land use decisions have a lot to do with soils at multiple scales. Hydropedology would stimulate better quantification of soil spatial and temporal variability that is based on mechanisms involved, including soil forming processes. Also, like I indicated earlier, hydropedology, of course, of course, would offer new perspectives in terms of how we might solve the total equation of soil formation. This would, however, require a lot of work, many opportunities, hopefully, along the way. And also, Pathology has a lot to contribute in terms of landscape scenario, like illustrated here, preferential flow at the landscape scale. And vice versa, advanced hydropathology, which enhance the use of pathologic expertise and promote better qualification in pathology. Excuse me. Just a few more slides to wrap up in terms of strategies for the vision I just described. I'll briefly talk about three listed here in terms of their relationship to CUAHSI. Illustrate here iterative loop into action of our three strategies that design scientific hypotheses, design of a set of scientific experiments to test the proposed hypotheses. Use hydrological observatories and natural laboratories using a good infrastructure and technologies, and then promotion and dissemination of hydropedology. We need an integrated network of hydropedologic observations that include hydrologic observations and soil observations across scales and our technologies that range from ground-based observations, point observations to global remote monitoring. In applying advanced remote sensing and geophysical tools, we need to strive to go beyond just empirical relations when converting geophysical or remote sensing data back to hydrologic parameters of interest. One way to input it is to insert hydropedologic insights to help constrain the inversion. Another clear need is to archive and share landscape water system data across scales and geographic regions to provide integrated systems. Illustrated here is an example of integrated CR-based non-point source pollution modeling system with various tools and databases working together. Here, unique contributions of hydropedology could include providing data such as flow pathways, enhancing model formulation and model selection, improving structural hierarchy and pattern identification, etc. Just a few words about expected scientific and societal impacts of our proposed vision. The moisture is the life-giving substance and is directly linked to the function of the Earth's critical zone. Nolan and Fredland summarize this adroitly as stated here. From Napoleon's defeat at Waterloo to increasing townfield in Kansas to greenhouse gas floods in the Arctic, the importance of the moisture is endemic to world affairs and merits considerable attention it receives from the scientific community. This importance can hardly be overstated, though it is often goes unstated. Here's another illustration in terms of a common question hydrogeologists will ask when dealing with groundwater quality and quantity. Is this question: where, when, how much, and how fast water and contaminants come from the overlying radon zone? Apparently, hydropedologists play a critical role in the environment. In the broader perspective, soils have 7+1 rows, as I sketched here, that range from Earth's critical zone to Mars exploration. In each of these rows, soil-water interaction is a critical factor. After all, when Mr. Soil and Mr. Water come together, you can imagine what miracles can happen. All right, to wrap up my presentation, here are the four aspects that I have touched in terms of the general idea about hydropedology and knowledge gap, and then our research vision, and then three interlinked strategies that are briefly touched and expected impacts. With that, I will stop here, and thank you for your attention.
Okay, thank you very much, and thanks to your team for all the effort that went into this.
You're welcome. Thank you.
At this point, let's open up to questions.
Ladies and gentlemen, if you wish to ask a question, please press star followed by 1 on your touchtone telephone. If your question has been answered or you wish to withdraw your question, please press star followed by 2. Questions will be taken in the order received. Please press star 1 to begin. Once again, ladies and gentlemen, if you wish to ask a question or you have a comment, please press star followed by 1. We'll hold a moment while we compile the list of questions.
Henry, I've got one to start.
Oh, thank you.
This is one that has been posted a couple times.
Okay.
People have asked me what the difference is between hydropedology and Pedology and Hydrology.
That's a good question.
There's almost a reluctance for a new term, or is there a difference, or?
That's a good question. I guess that's part of the reason why I, at the beginning in my introduction part, trying to elaborate a bit on the excellence of natural soils. Now, radon zone could be generally described that portion of the Earth's critical zone from the land surface to the water table. Now, hydropedology apparently would rely on its roots in pedology, where we considered pathogenesis, the soil formation, soil morphological features, and different soil types. Things like that, trying to utilize the pathological knowledge and experience to help understand how water will flow and chemical transport in the natural systems. And so, I guess perhaps you need to hear other comments. But perhaps hydropedology is part of radon hydrology. Radon hydrology may be more broad. But hydropedology is more focused, and but it depends on how people view in terms of their radon zone terms. Some may refer to just a deeper zone that would be in between the soil zone and the groundwater table, that kind of in between the unwanted zone that I indicated in one of my slides.
Right. Thank you. This is something that I wanted to ask. It's been asked to me a couple times now, actually.
All right.
There's a message in the chat box from University of Kansas.
All right. The question is, there's a long neglected area, but what about chemical reactions? I bring to the attention section at the Smith conference in May 2005 in Idaho, soils as the first factor in groundwater chemistry. Oh, that's good comment. Yeah, I certainly agree that chemical reactions or processes are very important in terms, particularly nutrient cycling, contaminant freedom, and water quality in general. If you recall, one of my statements was trying to emphasize pathogenesis as kind of integrated phenomena or holistic view of the system evolution, where physical, chemical, and biological processes come together. So pathogenesis include all of that, supposedly. Whether we do that nicely or not is a different story, though.
Okay. Anthony, are there any questions in the queue?
Yes, so we actually have a question from Xiaobang Chow. Please proceed.
This is Bruce Harrison at New Mexico Tech.
Yeah.
Hi. I really enjoyed your seminar. I have a use of soil taxonomy as a vehicle for modeling or transporting or transferring hydrologic properties in the landscape. There are two reasons I question that. One is the accuracy of maps, particularly when you get away from intensively agricultural areas. And secondly is the fact that the soil taxonomy itself is based essentially on soil fertility relationships rather than properties that may be more important in hydrology.
Well, certainly it's a very legitimate concern and good comments. I think, first of all, that statement about soil taxonomy presented here is a hypothesis. Whether it's going to work out the way that we thought it could, it's going to be tested, all right? But to directly answer your question, two aspects, in fact. The first one is the soil map, the soil database. If you recall, a couple of slides I was trying to indicate that soil maps actually have many different skills, many different levels of details of soil maps. Even the 20 or what we call circle soil maps often are not detailed enough, or in your words, accurate enough for what we might like to see in the catchment or more kind of localized field studies. All right. So, but that doesn't mean all methods are not useful. It's just a matter of how do we use appropriate formats to do the relevant applications. And in our catchment, for example, we developed much detailed format than the 20-level format, which I showed in one of my slides. That provides some useful information in terms of differentiating over the landscape in terms of moisture patterns. Of course, nowadays, whether countrywide is the digital circle or even statistical, that's more general than circle format. So we need to be cautious, in other words, when we use the format for certain applications. And so that's one. And the second aspect of your question related to taxonomic systems. In fact, at least supposedly, or what they have tried in terms of past pathologist efforts in developing taxonomic systems, either in the U.S. or in other countries, or in the FAO system, they have tried to incorporate physical, chemical, and biological processes, not just for fertility, but a lot more others. If you look at the taxonomic system, the soil properties that they use for develop diagnostic horizons, diagnostic properties, they are comprehensive, all right? But depending on your use of those taxonomic systems, of course, there are different perspectives on that. Now, in terms of whether they are going to be really helpful for hydrological applications, you're right that in the past, past pathologist efforts in developing taxonomic systems, they have not paid enough perhaps neglected to a greater extent hydrological aspects like hydraulic properties. Although they have some hydrological information like permitted K-set and that kind of label that way, and energy process and things like that, a lot of features that are related to morphology. But they did not pay enough attention to where we like to see now in terms of hydrological applications. But that doesn't mean we cannot explore into these existing systems to address what we are now interested in hydrological applications. So I hope that helped clarify the things.
Yes, I think it did. I agree with you entirely. I think that we need to spend a great deal of effort in trying to evaluate the use of soil taxonomy, because it is the database that is out there. They have a tremendous amount of information, and it would be reinventing the wheel to try and come up with some alternatives.
Right, I agree with you. That's why our team proposed that as one of our hypotheses. Yeah.
Thank you.
Thank you.
Once again, ladies and gentlemen, if you wish to ask a question or you have a comment, please press star followed by 1.
And I'm showing that it is just after the top of the hour, so we'll probably wrap up shortly, so this will be the last call for questions or comments. So I'd like to remind you that there is a discussion forum online. If anything comes to mind later that you'd like Henry or some members of the team to answer or respond to a comment about, feel free to do that. That's linked off of the Cyberseminar page.
Gentlemen, you have no further questions now.
Okay. So Henry, thanks again very much to you and your team.
Thank you all for your participation.
Thanks, everyone. I'd like to remind you that there are no seminars next week. The next one will be on Tuesday, November 30th at 3 p.m. Eastern. Take care, everyone.